In this module, we provide a high-level overview of the CUDA programming model. After watching this module, you will have an understanding of the basic CUDA programming concepts and abstractions, and how they are used to leverage the computational resources of GPUs for non-graphics applications. CUDA is a parallel programming model and software environment that exposes the computational horsepower of GPUs for non-graphics computing. In order to leverage the computational resources of the GPU with minimal effort, CUDA was developed with several design goals in mind. The GPU is a highly threaded parallel architecture containing hundreds of cores which collectively can execute thousands of concurrent threads. To fully leverage the computational resources of the GPU, CUDA must scale to hundreds of cores and thousands of threads. CUDA is designed to let programmers focus on the design of parallel algorithms rather than spend time on the implementation. CUDA is essentially a small set of extensions to the C programming language, so that the implementation of a parallel algorithm is straightforward. CUDA is also designed to enable heterogeneous computation, where applications use both CPU and GPU. Serial portions of an application are run on the CPU, and parallel portions of the applications are offloaded to the GPU. As such, CUDA can be incrementally applied to an existing application. The CPU and GPU are treated as separate devices with their own memory spaces. This configuration also allows simultaneous computation on both CPU and GPU without contention for memory resources. As mentioned previously, serial portions of an application are run on the CPU or host. Parallel portions of the code are executed on the GPU or device as computational kernels. A kernel is simply a function that is called from the host and runs on the device. Only one kernel can be executed on a single device at one time, and each kernel is executed by launching many concurrent threads, which execute the same kernel code in parallel. There are several distinctions that need to be made between CUDA threads and CPU threads. CUDA threads are extremely lightweight in terms of creation overhead and switching. Thousands of CUDA threads can be created in just a few cycles. As a result, there is no creation overhead to be amortized over the execution of a kernel, so that kernels consisting of just a few lines of code can result in performance gains. Thread switching is instant and therefore can be used to hide latency in memory loads and stores. One of the basic tenets of achieving good performance in CUDA is to exploit the nature of CUDA's lightweight threads by launching kernels with thousands of concurrent threads, essentially oversubscribing the processing elements, so that when a thread is stalled by a memory access or synchronization, it can be swapped out with no performance penalty. When a CUDA kernel is launched, it is executed as an array of parallel threads. Each thread runs the same code, and in order for threads to perform different work, each thread is given an ID that it uses to compute memory addresses and make control decisions. For example, this diagram depicts a kernel being executed by 8 threads. The thread ID is first used by each thread to access a different element of an input array. Each thread then passes its element of the input array to a function and uses the thread ID once again to store the result of an output array. In this example, each thread performs entirely independent work. In essence, this particular kernel is embarrassingly parallel. If threads of a kernel were limited to performing completely independent work, CUDA would be very limited in its application. Fortunately, this is not the case. The missing piece in the example on the previous slide is a means of cooperation between threads. Thread cooperation is valuable for several reasons. Threads can share results to avoid redundant computation, and threads can share data loads and stores from device memory, which can drastically reduce memory bandwidth requirements. Thread cooperation is a powerful feature in CUDA. While thread cooperation is desirable, unlimited cooperation amongst all threads in a kernel would have severe performance consequences and is not scalable. However, by limiting thread cooperation within batches of threads, CUDA achieves both thread cooperation and scalability. When a kernel is launched, the threads are arranged in a grid of thread blocks. Threads within each block can cooperate through shared memory and barrier synchronization, while threads in different blocks cannot cooperate. This arrangement allows programs to transparently scale across different GPUs. The ability of kernels to transparently scale to different GPUs results from the hardware being free to schedule blocks to execute on parallel multiprocessors, where a multiprocessor is simply a group of processors that execute one or more blocks of threads. For example, if we have a kernel consisting of 8 thread blocks and a GPU with 4 multiprocessors, the hardware can schedule each multiprocessor to run 2 blocks, whereas on a smaller device with 2 multiprocessors, the hardware can schedule each multiprocessor to execute 4 blocks. All this occurs without any modification to the source code. In both cases, the source code simply launches the kernel with 8 blocks. Although this diagram represents a fictitious example, real kernels with larger numbers of blocks can run well on hardware ranging from laptops to high-end servers, without modification of the source code. The previous slide used fictitious GPUs to demonstrate transparent scalability. This slide illustrates the computational resources on the 10 series GPU architecture. On the 10 series architecture, 240 thread processors execute kernel threads. These processors are grouped into 30 multiprocessors, with each multiprocessor containing 8 thread processors, 1 double precision unit, and shared memory, which allows thread cooperation. Each multiprocessor performs computations in SIMT, or Single Instruction Multiple Thread fashion. SIMT is similar to SIMD, or Single Instruction Multiple Data, except that SIMT is a bit more flexible in that each thread is executed independently with its own instruction address and register state. SIMT enables programmers to write thread-level parallel code for independent scalar threads, as well as data parallel code for coordinated threads. CUDA kernel threads have access to a variety of memory spaces which differ in scope, size, lifetime, and latency. Each thread has read and write access to per-thread register memory, which is on-chip and exists for the lifetime of the thread. In the 10 series architecture, there are 16,384 32-bit registers per multiprocessor, which are divided amongst threads in all resident thread blocks. Unqualified variables that do not fit in registers reside in local memory, which is uncached in DRAM. The lifetime of both register and local memory is the lifetime of the thread. All threads within a block have read and write access to fast on-chip shared memory. In both 8 and 10 series architectures, 16 kilobytes of shared memory are divided between all resident blocks on a multiprocessor. The lifetime of shared memory is the lifetime of the block. All threads have read and write access to the same global memory, which is located in the device DRAM. Global memory is large, up to 4 gigabytes, uncached, and exists for the lifetime of the application so that it is persistent across kernel launches. In addition to kernel thread access to global memory, the host has read and write access to global memory. As such, global memory is used to transfer data between the host and device for kernel input and output. The kernel memory access on this slide is a depiction of the memory access for programming abstractions such as threads, blocks, and kernels. It is useful to complement this depiction with a physical layout of these memory spaces. The physical layout of various memories is shown on this slide. On the chip, we have the fast register and shared memories. In device DRAM are the local and global memories. Local memory is local in scope. It is local to a thread, but physically it resides in the device DRAM. From a performance perspective, one wants to leverage register and shared memory in order to minimize use of local and global memory. One should note that data transfers to and from the host go through global memory only. An application cannot read or write to shared memory directly. The execution model for CUDA, starting at the smallest scale, is that threads are executed by thread processors. Thread blocks are executed on multiprocessors. Each thread block, once assigned to a multiprocessor, does not migrate. Several blocks can reside concurrently on a multiprocessor, which is desirable from an efficiency standpoint as thread switching is used to hide memory latencies. The number of blocks that can concurrently reside on a multiprocessor is limited, however, by the multiprocessor shared resources, namely the number of registers amongst all resident threads and the amount of shared memory partitioned between all resident thread blocks. Kernels are launched as a grid of thread blocks, where only one kernel executes on a device at a time. CUDA has several advantages over legacy GPU, where generic computing operations are mapped onto the graphics pipeline. In CUDA, memory access is much more flexible than GPU. Threads can access any memory location as often as needed. CUDA threads can cooperate within blocks through shared memory and thread synchronization. Significant bandwidth reduction to device memory can be achieved when threads in a block cooperatively load data into shared memory, where any thread in the block can access any shared memory location. Another advantage CUDA has over legacy GPU is that CUDA has a low learning curve. CUDA consists of a few extensions of the C programming language, and no knowledge of a graphics API is required. CUDA does not just hide the programmer from a graphics API, but has been designed in both software and hardware to perform a different route to the computational resources, thus avoiding the performance penalty that would be realized if it were simply a software layer that sat on top of the graphics layer. In summary, there are several key abstractions in CUDA which allow a programmer to easily and efficiently harness the computational power of GPUs for non-graphics applications. The first abstraction is that CUDA makes use of many lightweight threads. Over 1 trillion threads can be launched in a CUDA kernel. The negligible overhead associated with thread creation and switching permits the granularity of parallelism to be very small without impacting performance. This results in a very simple data decomposition model. A unique thread ID is used to access array elements and perform computations on these elements. CUDA has a simple 2-level hierarchy of concurrent threads. Threads are batched together in blocks, where the independence of thread blocks gives the hardware great flexibility in scheduling threads and results in excellent scaling using this simple execution model. Within a block, threads have the ability to cooperate. Threads within a block can synchronize through a lightweight barrier synchronization. Threads can also share data and thus global memory accesses through per-block shared memory. This thread cooperation within a block provides simple synchronization and communication models.